Hello. I've spent most of my day so far recording for MA 266, but we're going to step back for a second and record the last exam, or at least the midterm one material for 265's Spring 2017 final. Question 1. Let m and n be greater than 1, they're two natural numbers such that m is greater than n. Which of the following is true? Okay, a linear system of m equations in n variables, so more equations than we have variables, is always consistent. Well, let's try this out. Let's do a case where we have two equations and one variable. So how about 1x1 equals 1 and 2x1 equals 1. This system right here is not consistent. If we take this one to be true, this one necessarily is not. So we can just, for most of these too, we can make little examples for ourselves to see why these don't or do have to work. Okay, number 2, a linear system of n equations in m variables is always consistent. So how about we do 1x1 plus 1x2 plus 1x3 is equal to 1, and then 1x1 plus 1x2 plus 1x3 is equal to 2. Yet again, we have a situation where we're doing this. We have fewer equations than we have variables, but we've shown that there's a case where it does not have to be consistent. Okay, 3, a linear homogeneous system of m equations in n variables always has infinitely many solutions. So more equations than we have variables, so it will be taller than it is wide. And they're saying that always has infinitely many solutions. So let's go back to the one variable, and let's go 3 equations this time. One variable, 3 equations. x1 equals 1, 2x1 equals 2, and x1 equals 3. Yet again, you can see how we do not have infinitely many solutions here. We only have one solution. Or sorry, getting carried away. We don't have one solution. We have no solutions because our system is inconsistent. Okay, finally, a homogeneous linear system of n equations in m variables will always have infinitely many solutions. So this is saying that we have more variables than we have equations. So our matrix will be wider than it is tall. And let's see what we can set up for this. How about 1x1 plus 1x2 plus 1x3 is equal to 0, and 1x1 plus 2x2 plus 2x3 is equal to 0. Well, in this case, this is actually true. This, no matter how you set this up, for one, the 0 vector will always be a solution for however many variables we put in, and also we'll be unable to fully define, like the system is underdefined because we only have 2 equations, 3 variables. One of these variables is going to be free at all times, which means that we will have infinitely many solutions. So 4B is our only correct answer choice. Question 2, consider this linear system of equations. Under which condition will the system be consistent? So essentially, what we're going to be doing is setting this up and solving it to the point where this entire bottom line here is all zeros, and it's equal to some expression of a, which also must be 0. So let's go. 2, 1, negative 1a, 1, negative 1, 2, 1, 4, negative 1, 3, a squared. Let's see what we can do with this. Okay, let's subtract 2 row 1s from row 2. That's going to give us 0, -3, 5, and a squared minus 2a. Subtract 2 row 2s from row 1. We will get 0, 3, minus 5, and a minus 2. And let's see what we can do with this. Oh, okay, now this is looking pretty good. Let's add row 1 to row 3. 0, 0, minus a, and then minus 2. So we see that we have this to the point where this expression right here must be equal to 0 in order for our system to be consistent. If this is non-zero, by definition, our system is inconsistent. So a squared minus a minus 2 must be equal to 0. A minus 2, a plus 1 is equal to 0 factored. So a is either equal to 2 or -1. So D is our correct answer. Question 3. Let A and B be two 4x4 matrices. Which of the following statements is always true? Okay, option A, if A plus B is singular, then either A or B is singular. So a lot of these statements that they'll make, they sound like they very well could be true. And it's kind of difficult to test them, especially with 4x4 matrices. But it's pretty fair to say that if you can't think of some basic fact that we've learned in class, it's likely not true. So both A and B fall under this category. If AB is symmetric, then BA is also symmetric, or a symmetric matrix is just equal to its transpose. Both of these sound good, but they are not necessarily true. And I wish I had a nice proof for you, but you'll see that there just is one answer here that does make sense over all the other ones. One important thing to note for D is that we do not know if A is invertible. If A is invertible, then we could multiply both sides on the left by, I'll zoom in here, by A inverse, and we would get B equals C, but that's only if A is in fact invertible, which we don't know if it is. So D, we are unsure about. That's sometimes true, but not always true. And then E, if AX equals B is consistent for some B not equal to 0, then A is non-singular. Well, you can think of this just purely in the conceptual sense. If you have a matrix whose determinant is 0, you can think of the transformation represented by that matrix as a transformation that smushes the input space into some lower dimension. So it is still perfectly possible to have a transformation that takes 3D space. In fact, we can set one up here that takes 3D space, takes in 3D space, and outputs a line. That's what this transformation would do right here. But it's important to note this is consistent for some B's, just not consistent for all B's. But this matrix is in fact singular, and you can see that just by multiplying the elements on the diagonal, because we are in an upper triangular form. So E is incorrect. That leaves us with C. If A and B are similar matrices, which means that you can equate them just by using elementary row operations, namely adding rows, adding factors of rows to other rows, then the determinant of A is equal to the determinant of B. Well, we know that when you add a multiple of a row to another row, it doesn't change the determinant at all. So because we can equate these two just by using those elementary row operations, the determinants must be equal. So 3 is in fact C. Let's assume that a 4x4 matrix A is row equivalent to B here. Which of the following statements is true? Okay, A, B is not in the reduced row echelon form of A. Well, it looks like It looks like it is. We have a leading term here. We have a leading term here, pivot positions, and all above them are all zeros. All below them are all zeros, and they're all ones, and we get this stair-step shape. So A is untrue. We are in a reduced row echelon form. B, the determinant of A is 0. Well, we can find the determinant of B by multiplying all the elements on the main diagonal of B. We'll see that the determinant of B is equal to 0. And that's important because A is row equivalent to B. So A's determinant must also be 0. So B is incorrect. What about C? The null space has a dimension of 3. Okay, we have a formula for this. The number of columns equals the rank of the matrix, or the number of pivot positions, plus the rank of, or the dimension of the null space. So setting that up, we see that 4 columns is equal to 3, the rank, plus, well, the dimension of the null space has to be 1. So it's definitely not 3. And what about this? The dimension of the column space has a dimension of 3. Well, that is true. We just said that the dimension of the column space, which is the same thing as rank, oh, sorry, I read that wrong. No, it is false. The dimension of the column space is 3 because we have three pivot positions. Okay, E, if AX equals B is consistent for some B not equal to 0, then it has infinitely many solutions. Well, you can think about what this matrix is doing, because it has 3 pivot positions and it has 4 columns, as taking in all of 4D space as an input and outputting 3D space as an output. So for every point I'll actually draw it out. So we got our domain and our codomain, which are actually the same dimension. So 4D, 4D, and we have a 3-dimensional range inside that. For any input that actually maps to our output space, we'll have an infinitely many number of points that also get squished into that space, because we're going down a dimension. We're going from 4D down to 3D. So E is our correct answer for 4. 5, let's consider this linear system. For which value of A does the system have infinitely many solutions? So let's just set this up. We have 1, 1, 3, 3, 0, 1A, negative 1, and 2, 3A squared, 2, 3A squared, A plus 2. So we should be able to copy this over, do some row operations, and get to something that we can solve. So let's subtract 2 row 1s from row 3. We get 0, 1, A squared minus 6, and A minus 4. In order for us to have a free variable so that we have an infinite number of solutions, these two are already equal to each other, the elements of the second row and the third row in the first 2 entries. But we would also want A to be equal to A squared minus 6, and we would want A minus 4 to be equal to negative 1. So just from this guy, we can see that A is equal to negative 3, but also if we go over here, A squared minus A minus 6, A plus 2, A minus 3. And so this gives us 2 options here, but we see that only A equals 3 works for both of our conditions. And if both of these conditions are true, then we would have 3, 3, negative 1, and we can turn this into a row of zeros, and there's our infinitely many solutions. So 5 is D. I'm going to move this out of the way. There we go. 6. If the determinant of that matrix right there is 6, we're told to find the determinant of this matrix. So first off, we can see that multiplying this row by 2 and multiplying that row by column by 3 is completely negated by dividing this row by 6. And so we can cross out all of this all of this scalar multiplication, because in the end, all that's doing is multiplying by 6 and then dividing by 6. Then we're left with C1, C2, C3, A1, A2, A3, B1, B2, B3. Okay, so we definitely want A1 to be in this position, and actually, no, we're going to do this in a slightly different order. We're going to have to transpose this matrix so that these entries read 1, 2, 3 along the top instead of 1, 2, 3 down like they've done here. So transposing the matrix does not change the determinant. So the determinant of this is the same as the determinant of B1, B2, nope, whoops, is the same thing as the determinant of C1, C2, C3, A1, A2, A3, B1, B2, B3. And now all we have left to do is switch the A and the C rows and then switch the C and the B rows. And we will have reached this matrix right here. And we know that switching a row is the same thing as negating the determinant, so we've done that twice. So overall, the changes that we've done to our matrix is dividing it by 6, multiplying it by 6, multiplying it by -1 twice, and all of this was done to the number 6, and our answer is A, just 6. A little bit anticlimactic, but whatever. Question 8, if A is equal to the matrix given there, then the 2-1 entry of A inverse is what? So, in order to find the 2-1 entry of A inverse, we need the determinant of the overall matrix, which is going to be 4 multiplied by the determinant of this submatrix, which is -1. So -1 over 4, and then we know that we need the what do you even call it? I can't even remember the word. If this is the ij entry of the matrix, we're going to need the determinant of the submatrix for the ji entry. So 2-1 is here, so 1-2 is up here. So we'll cross out the row and the column that guy is in, that position is in, and write down the determinant of its matrix 1, 1, 1, 0. Its determinant is 1, but we also have to remember that there's a scheme of signs, so plus, minus, plus, minus, plus, minus, plus, minus, plus, that goes along with this that we have to take into account, and this position here will have a negative sign, so we have to multiply everything by -1, and so that will give us 1/4, and 8 is B. Question 11, determine all the values for C such that the following vectors form a basis of R3. So if we have 3 pivots, we know that these 3 vectors are linearly independent, and since they form a 3x3 matrix together, we know that they will span R3. So -1, 0, 1, 4, 2, 4, 2, 1, C. Let's start messing with this. Let's add row 1 to row 3, 0, 8, C plus 2, and let's subtract 4 row 2's from row 3. And we see that if C is equal to 2, then we do not form a basis because we'll have a row of all zeros, so therefore only 2 pivot positions. But if C is not equal to 2, then we're good, and we have 3 pivot positions. So 11 is E. 12, find the rank of the following matrix. 1, -1, 3, 2, 4, 7, 2, 1, -1, -10, 7, 5. Let's get started by subtracting 4 row 1's from row 2. We will get 0, 11, -10, -7, and let's add row 1 to row 3. We will get 0, -11, you can see where this is going, 10, and 7. If we use, now we can just use one of these rows to cancel the other out. I'm going to add row 2 to row 3, get 0, 0, 0, and there we go. We can see that since we have two pivot positions, that these are the two positions that will become leading ones in the row echelon form. Our answer is C for 12, because we have two pivot positions, two leading entries. Okay, hopefully that was helpful. I went a little crazy trying to do this 5x5 determinant. I'm sorry if that's what you're here for. It upsets me more than it upsets you. Let me know if I got anything wrong or you have any suggestions.